Hello everyone, let's take a look at this problem from the OpenStax book about vector addition. Suppose you first walk 12 meters in a direction 20 degrees west of north, and then 20 meters in a direction 40 degrees south of west. How far are you from your starting point? And what is the compass direction of a line connecting your starting point to your final position? So this is about adding two vectors, right? So the first part of your trip you can call the vector A, and the second part of that trip, call it vector B. Adding A to B, vector addition, will result in R, right? Where you end up at the end of this trip. Now, there are different ways to add vectors. One is to do it graphically. So if you grab a protractor and a ruler, if you use graph paper and are very precise, you can do this just using that, right? So you can use the graphical way of adding vectors and do this problem. But I want to talk about a more mathematically rigorous way of possibly doing this, is to use the idea of unit vectors, and you'll see kind of the benefits of doing it this way. So let's take a look at this. I'm going to redraw the coordinate system, x and y. And one of the things you have to do is translate north, south, east, west, those directions into your Cartesian coordinate systems. If you just imagine you are looking at this from a bird's eye view, positive y could be your north direction, and positive x could be the east direction. So even though they're saying you're moving north and east and directions like that, you want to translate that to x and y. So here's our coordinate system, and what I'm going to do is just look at the first vector, A, and just draw that only, just to take a look at that. So vector A looks like that. All right, so I'm just translating what I'm having in the problem diagram into my own diagram, and I can put in the angle, which is 20 degrees, and they also tell me the magnitude of this vector is 12 meters. Now what I want to do is to break this vector up into its component parts. What I want to show you is how to do that. Okay, I'm going to copy over the vector A here to the side. That's A right there. And what I can do is break up this vector A into its component parts. Given this vector A, you can see that there are two components, x component and a y component, that makes up this vector, right? So imagine just adding this vector to this vector, then you get vector A, right? So it's made up of two components. So you can write mathematically vector A is equal to ax I hat plus ay j hat. Right? And the way we're going to figure out what these components ax and ay are is we're going to use some trig to help us out. So we know this is 70 degrees, given that the other angle is 20 degrees. This has to be 70 degrees. Now we can use a little bit of trig. So the mnemonic to remember is SOHCAHTOA, to remember which trig functions are which. So SOHCAHTOA, and if we write that the cosine of 70 degrees is equal to ax divided by a, right? So for 70 degrees, the adjacent, right, is ax, and its hypotenuse is a, right, the magnitude of a. So if we solve for this, we can solve for ax is equal to a cosine of 70 degrees. And working that out, ax is equal to 12 meters cosine of 70 degrees. That's equal to 4.104 meters. So we found one component of this vector. We can find the other component, the ay component, using sine of the angle, right? So sine of 70 degrees is equal to ay over a, right? So for this angle, opposite is ay, and a, the magnitude of a, is its hypotenuse. So we have sine of 70 degrees is equal to ay over a, and again, we can solve for ay, which is equal to a sine of 70 degrees. So ay is equal to 12, right, the magnitude of a. Sine of 70 degrees is equal to 11.276 meters. As a reminder, just make sure your calculator is set to either degrees or radians, depending on what you're using. So in this case, we're using degrees, so make sure it's set to degrees, otherwise it won't give you the correct answer. All right, so we have the two components of A, so we can go ahead to our original diagram and put down what is A. A is equal to, and we have to think about the directions, right? So even though we got a magnitude for AX, it's actually, AX is actually pointing to your left, right? So that should be negative 4.104 meters in the I hat direction plus 11.276 meters in the j hat direction, right? So that's what is A. Okay, we've taken this vector, given the information that the problem told us about, and we have now written A in its ij component form. And take a moment to think about the signs, right? So the I hat component is negative because to make up the vector A, you have to travel from the origin in the negative direction of x, right? And so it should be a negative number, and then to make up the vertical part, you have to go up, right? So which is the positive direction. So the 4 is a negative number, the 11 is a positive number. So we worked on A. We still have to add these together, A and B, so what we're going to do is do the same thing for B, right? So draw B as given, break it up into its component forms, and then we can get to adding these two vectors together. So one thing about vectors that's kind of handy to use, depending on the problem, is that vectors can be moved as long as you don't make them longer or shorter, and as long as you don't change its direction. If you pick up the vector A and just slightly move it to the right, it's the same vector. It behaves the same way. So even though vector B starts right at the end of vector A, what we can do is just move it for our diagram so that it is starting at the origin, right? So what I mean is I can draw vector B like this. Okay. So it might look different. You might say, well, it's in the wrong place. So the point is that a vector cares about its length and its direction, right? So if I keep the same information in terms of the length and the direction, then the B as given in the problem and the B I've drawn here in my work, they're exactly the same. It just makes it a little bit less cluttered when you draw it this way, right? So I want to kind of, the objective here is to break down B into component parts, so this makes me see this a little bit better. So I can say that this angle is 40 degrees, its length is 20 meters. Okay, so I'm going to go through the same process I did for A to break down vector b, right? So let's redraw vector b, and you can break up the vector into its components, right? So when I'm breaking up vectors into components, notice I'm following x and y, the coordinate system, right? The lines that I'm drawing are not random. It's not any two lines that connect to A. That's not the idea. The idea is when you're breaking up A or B, you are breaking them down in the same direction as the coordinates that you have, right? So you have a certain component bx going in that direction, and then you have a by going that direction. So together, if you add them together, that's what makes up b. So b generally can be written as bx I hat plus by j hat. Again, using a little trig, we want to find out what these components are. That's 40 degrees right there. So then cosine of 40 degrees is equal to bx over b, right? So looking at the angle 40 degrees, cosine of that adjacent is the bx, the hypotenuse is the magnitude of b, right? So that means we can solve for bx is equal to b cosine of 40 degrees. So bx is equal to 20, the magnitude of b, cosine of 40 degrees, which is equal to 15.321 meters. So that gave us bx. Let's find the other component, by. So sine of 40 degrees is equal to by over b. Right, so looking at that angle, what is its opposite, by? What is its hypotenuse, b? Right, the magnitude of b, which lets us solve for by is equal to b sine of 40 degrees. So by is equal to 20 meters, the magnitude of b again, sine of 40 degrees, which is equal to 12.856 meters. Okay, so we have the parts. Let's put it together. So going back up here to our original diagram, we can now add what b is. B is equal to minus 15.321 meters in the I hat direction, minus 12.856 meters in the j hat direction. Okay, so they have to both be negative, right? So when we're doing the trig, we're setting this up just for the magnitudes, right? We're just looking at the sides of a right triangle, right? So there's a right triangle here. So we're just looking for the sides of the right triangle. We're not really particularly caring about the signs, right? What's positive, what's negative, just yet. And then when we're coming back here to say what are the vector components of b, then pay attention to the signs, right? Because b is pointing downward and to your left in our coordinate system. That means what x value does it have? It has a negative x value. You have to travel from the origin in a negative x direction, and to get to the end of that vector you have to go in a negative y direction to get to the end, right? So that's why both of the components here are negative, as opposed to in A, one of the components was positive because you moved in the positive y direction, right? It just depends on which way the vectors are pointing. Okay, so the objective was to add these two together, A and B. So let's see if we can do that now, since we have the component forms. And the nice thing about unit vectors and dealing with them is that when you have to find the result, which is equal to A plus B, all you have to do is add I hat to I hat, right? So if you just add the components, not making sure not to mix the components, right? So you can't add I hats to j hats. So as long as you're adding the i's together and then the j's together, then that's all there is to it. So let's do that. So a plus b, what we have to do is grab all the I parts and add them together. So negative 4.104 meters minus 15.321 meters. That's the I hat part. And then we do the same thing for the y's, which is 11.276 meters minus 12.856 meters in the j hat direction. And if you did that, you should get minus 19.425 meters in the I hat direction, minus 1.58 meters in the j hat direction. So that's it. That's all you really need. If somebody asks you what is the result of adding A to B, you can just list this, and that's the end of it. You can be done, because in this way you are telling somebody both the magnitude of the vector and the direction of the vector, right? But if you want to kind of visualize a little bit, because the problem is getting at doing this graphically, if you want to visualize it, you can still do that, right? So taking the result here, you can look at the vector components and then redraw what r should be, right? So we have a negative component in the x direction, right? So let's say we're starting right there, moving in the negative direction by 19.425 meters. And then we also move in the negative j direction, so 1.58 meters. And if you did that, the result looks like that, right? So that's what the result r looks like. And the nice thing about the ijk unit vector convention is that you're always setting up a right triangle, right, when you list these components. So if you ever want to find the result, its magnitude, all you have to do is use the Pythagorean theorem. So you take 19.425 meters, square it, add that to the square of 1.58 meters, and you should get 19.5 meters, and that's the magnitude of the vector r. Now, you might want to know what that angle is as well, right? So when you add a to b, r shows up here, but it's slightly dipping below that x-axis by some angle, so you want to know what that angle is. And we can do that too. So let's redraw our diagram here of r. So here's r. The components are 19.425 meters and 1.58 meters. And again, it's a right triangle. And there's an angle here that we can solve for. And how do we do that? Again, using our friendly SOHCAHTOA, right, a mnemonic for remembering our trig functions. So if you take the tangent of theta, opposite over adjacent, we have 1.58 meters divided by 19.425 meters. Take the inverse tangent or arctangent, and you should get 4.65 degrees. Okay, so just showing you how you can do this problem in a different way, because the intention of the problem is to do this graphically using a protractor, using a ruler. But even though it seems like more complicated doing it this way. This is the more mathematically rigorous way of adding vectors. And the advantage here is that once you have more than two vectors, 3, 4, 100, imagine trying to do 100 vector additions graphically. It would take a long period of time. So this is much better, right? So you're seeing that if you break up the vectors into components, x and y, or I hat and j hat components, then it just makes it much more straightforward. All you have to do is add the x components together, add the y components together, and that gives you the addition of a plus b.